Welcome to This Explainer. Okay, today we are tackling a massive question. How do devices actually manage to establish reliable, structured communication over the literal chaos of the internet? We're diving deep under the hood of TCP, the Transmission Control Protocol. We're going to get into the protocol logic, those key variables, the header fields, the whole shebang. And by the end of this, you're going to have exactly what you need to absolutely crush your upcoming GATE exams. Let's get into it.
Real quick, here's our roadmap for today. We're covering TCP connection basics, the famous three-way handshake, decoding sequence numbers, TCP state transitions, network sockets and multiplexing, and finally, we'll wrap up by applying all this to solve some real GATE exam questions.
All right, Section 1, TCP connection basics. Starting communication.
Okay, so before a single drop of data can actually flow over the network, these devices need a starting point. And the really crucial thing to grasp here is that both sides don't just, start counting at zero. Actually, when the SYN flag, which stands for synchronize, is turned on, both the TCP client and the server generate a totally random initial sequence number, or ISN. You might be wondering, why random? Well, if sequence numbers were predictable, malicious actors could literally just guess them and hijack your entire session. No way we want that. So this random ISN securely kicks off the conversation and establishes a unique mathematical baseline for us.
Moving right along to Section 2, the three-way handshake, establishing trust.
Now that we've got our starting numbers, let's look at exactly how they're exchanged. It's actually a brilliantly orchestrated protocol. It uses this strict three-step dance to establish mutual trust. It's kind of like picking up a phone and saying, hey, are you there, right? So here on the network, the TCP client kicks things off by sending packet 1 across the wire. This packet has the SYN flag explicitly set to 1, and it carries the client's unique initial sequence number. Let's just call it X for now. And notice, the payload here is 0. There is absolutely no user data in this packet. It is 100% just for connection setup.
So the server hears this hello and has to prepare its response. It needs to tell the client, hey, I got your packet. It does this by calculating an acknowledgement number. Mathematically, this is incredibly simple but absolutely vital. It takes the client's ISN, which was X, and literally just adds 1 to it. Boom, the acknowledgement number becomes X plus 1. And this perfectly illustrates the second phase of our phone call analogy. I hear you, and hey, I am here too. The server packages this up and sends back packet 2. In this one, it sets both the SYN flag and the ACK flag to 1. It includes that acknowledgement number of X plus 1 that we just figured out, but it also includes its very own randomly generated server initial sequence number. And let's just call that one Y. Finally, the client gets this and essentially says, awesome, let's talk, by sending packet 3. In this very last step of the handshake, the client sets just the ACK flag to 1. And the acknowledgement number it sends back? You guessed it, it's the server sequence number Y plus 1. And just like that, our three-way handshake is complete. The TCP connection is officially established, and data can finally flow in both directions.
Let's jump to Section 3, decoding sequence numbers, operational logic.
Let's isolate the operational logic we just saw because honestly, you absolutely must memorize these rigid rules for your exams. First, like we just saw, a SYN segment does not carry any user data, 0 payload. Second, and this is the big one, even though it carries absolutely 0 payload, it mathematically consumes exactly 1 sequence number. This rule is the whole reason why the acknowledgement formula is always the sequence number plus 1. It's acknowledging the invisible space that the SYN flag took up. Kind of mind-blowing when you think about it.
Which brings us to Section 4, TCP state transitions, connection lifecycle.
So behind the scenes, every single time a packet is exchanged, the operational states of these machines are actually changing, and they map precisely to the SYN, SYNAC, and ACK packets we just broke down.
Let's flow through this step by step. We start at closed. Then the server moves into a listen state, just patiently waiting for a client to reach out. When the client fires off that first SYN packet, it enters the SYN_sent state, while the server, once it receives it, jumps into SYN_received. And finally, once that last acknowledgement is processed, both sides get to rest at the absolute holy grail of states, established. This is it. This is the only state where your actual application data can start flowing.
Up next, Section 5, network sockets and multiplexing. Multiplexing basics.
Now, before we hit the exam questions, we got to understand where this data actually enters and exits the application. We've been talking about the network, but how does the software plug into it? Well, this is exactly where sockets come in. Think of a network socket as simply a door to your application. It bridges your specific software process to the OS's transport layer. From a technical standpoint, it's really just a data structure operating as an object right there in your machine's memory. And to communicate, two distinct network processes need a paired set of these sockets. You've got one socket over on the client side, one on the server side. Each endpoint acts as a dedicated gateway for two-way communication. When developers write the code to create these doors, they have to declare the underlying protocol. If they want a super fast but, unreliable UDP door, they create a datagram socket, known in code as sock_dgram. But for the rock-solid, highly reliable sequence track TCB door that we've been geeking out over today, they create a stream socket, or sock_stream.
And this entire setup is the foundation of multiplexing. Right now, your computer probably has dozens of these sockets open at once. Your browser, your email, some background update doing its thing. The transport layer's job is basically to act like a giant traffic cop. It aggregates all these messages coming from multiple different network sockets, slaps the correct protocol headers on them, and cleanly merges them down into the network layer to be sent out over a single physical wire. Pretty cool, right?
Okay, Section 6, Solving Gate Exam Questions, Applying TCP Logic. It is time for the boss battle. Take a look at this multiple select question from Gate 2024. It asks, if NP is the sequence number in the SYN from client P to server Q, and NQ is the acknowledgement number coming back in the SYNAC, what is the relationship? Pause for a second. Think about it. Do you remember our strict rule about the SYN segment? Right. It consumes exactly one sequence number. Therefore, for sure, the correct statement is that the acknowledgement number NQ absolutely must equal NP plus 1. If you know that core rule, the math is literally instant.
Let's look at one more, a fully worked out Gate 2025 solution. Examiners absolutely love testing your knowledge of the header flags during the handshake. Remember, Packet 1, our initiator, has its SYN flag set to 1 and ACK set to 0. But Packet 2, the server's reply, has both SYN set to 1 and ACK set to 1. Knowing this exact sequence of zeros and ones is the specific tactical knowledge you need to isolate the correct options immediately and grab those marks.
You guys have done great today, but before we wrap up this explainer, I want to leave you with a slightly provocative thought to ponder. We just learned that the operational logic of the TCP handshake requires the server to transition into a SYN undeceived state, right? And we learned that it literally allocates memory for network sockets while it's waiting. So what do you think happens to a server if a malicious attacker intentionally sends thousands of initial SYN packets but purposefully never sends that final packet 3 ACK? Well, this is the exact foundation of a devastating cyber attack known as a SYN flood. And understanding the TCP logic we covered today, that's your very first step to learning how to stop it. Keep exploring, keep questioning, and I'll catch you in the next explainer.